Hi people and welcome to this video. In this video, we'll be working on the probability section of the Mathematics Paper 1 for May-June 2026. Okay, so we're on question 10 and 10.1 says, Dr. Calculus's wardrobe has ties and we have trousers and shirts. Okay, so there are 6 blue ties and red, green, so they're different colors. Okay, but they still count as ties. So these are just the different types of ties that he has, and then trousers and then shirts. So 10.1.1 says, an outfit comprises of a tie, trousers, and shirt. Okay. How many different outfits are possible from the items in the wardrobe? Okay, so this is a case of counting principles. We can think about it like this, okay? One outfit, to create an outfit, we need the following combinations, okay? We need to have a tie, we need to have a pair of trousers, and then we need to have a shirt. So we can look at the number of, things that he can have in each of these little categories, but then all of this make up an outfit. So on this side, I'm going to put the ties. I'll just label it on top so you know what we're working with there. So that will be for ties and then trousers and then shirts. Okay, so the total number of outfits he can create, just think about ties, okay? How many options of ties does he have? He has 6 blue ties. Okay, that's 6 ties there. He has 4 red ones and 5 green ones. So we add these up together. 6 plus 4 gives us 10 and then plus 5 is 15. So he has 15 options with ties. They haven't created any restrictions. So we're just going to look at the total items that he has in each. And then trousers. How many trousers? He has exactly 4 trousers. So we're going to say that's 4. And then, so I put this on the bottom really, 15 and then 4. And then the shirts. How many shirts does he have? He has 3 red, so now we have to just calculate that. So 3 plus 3 is already 6 with the 4, okay, is 10. And then we have 2 and 4, which is 6, so 16. Okay, so there we'll have 16. Okay, so right at the end. And if you multiply these, you're going to find out the total possible outfits that he can create with this. So this is 15 times 4 times 16, and that gives us 960. So he can create 960 outfits, and that is our answer. Moving on to the next question. Then the next question says 10.1.2, how many different outfits are possible if Dr. Calculus does not wear red and pink at the same time? Okay, so he's not going to wear red and pink at the same time. He can wear red and red. They're not saying he can't wear red. He just can't wear red and pink at the same time. So what we can do is find out the total number of outfits that he's going to have where he's going to have red and pink at the same time. And then we can remove that from the total outfits. And then that would give us the total number of outfits without red and pink. So we're going to look at the case of outfits with red and pink. Okay, so let's see what kind of outfits can he create with red and pink. So remember that an outfit is created with these 3 items, okay, the tie, the trousers, and then, the shirts. So where red and pink will be together. So in this case, the ties, do you see that he has 4 red ties? So we're only going to look at this. I'm trying to specifically take out the outfits where he wears red and pink at the same time. So we're going to have a situation where he wears any of his 4 red ties. So for the ties, we're just going to put 4. And then in the trousers, he can wear any of the trousers because remember, a full outfit must have a tie, a pair of trousers, and a shirt. So as long as he wears red and pink with any of these trousers, then he's wearing red and pink. And so we want to remove that. And so for the trousers, the total trousers that he has is 4. So if he wears red and pink with any of these 4 trousers, then, it's a problem. And then over here, because he's wearing red, we need to ensure that he can't wear pink. Okay. So how many pinks are there? There are 2. So we're going to say 2 over here. So we're saying 4 times 4 times 2. And then that would give us the total outfits that include red and pink together. So let's find out what that is first. So the total outfits with red and pink. Okay, 4 times 4 times 2 is 32. So this is 32. And so the total outfit where he does not wear red and pink you take the total outfits that he can make up with all his clothes, remove the ones with red and pink, and that will give you the ones that don't include red and pink. Okay, so outfits without that. And so you're going to just say the total 960 minus the 32 outfits, and we can get our answer here. Okay, so that is just going to be 928. Okay, so a total of 928 outfits. Moving on to the next question. And then 10.1.3 says, calculate the probability. So it's not just the number of outfits here. So probability, remember you're going to put whatever you find over the total number of outfits he can create, okay, which we know is a total of 960. So calculate the probability that only blue and black items will be used in an outfit. Okay, so now we're looking for outfits where he's only going to have blue and black. That's all we're allowed to pick. So for ties, okay, you see that here he has 6 blue ties. So these are 6 ties that he can use out of all the ties that he has. And then for the trousers, you see that he has 1 blue trouser and a black trouser. So we need to include both, meaning for the trousers, he has 2 trousers he can wear. And then for the shirts, blue, okay, we don't have black. So just 3 blue. So 3 shirts that he can use there. So that is going to be 6, 2, and 3. So 6 times 2 times 3, and that will give us our answer. Okay, that will give us that numerator. So let's just get the outfits first with only blue and black. Okay, and this is just going to be, we say 6 times 2, and then that one was, he had 3, okay, 3 blue shirts. So this is finally equal to, that's just going to give us 12, and then 12 times 3 is 36. So finally, the probability of outfits with only blue and black. I mean, you could have just said blue and black. It's not a problem. Okay. And then this is just going to be equal to, you're just going to say it's that 36 over the total number of outfits he can create in his wardrobe, and that is 960. Okay, so I know that can definitely simplify. So 36 over 960, I'll just leave it as a fraction. Okay, so this is going to be 3 over 80. I don't want to leave it as a decimal because, then we must round off, and I just want it to be as accurate as possible. So there we are. So 3 over 80 is our answer there. And that is it for that question. Moving on to the next question. Okay, we are on question 10.2, and 10.2 says, a survey was conducted among 54 people to determine which of the 3 types of tea, A, B, or C, they drank. The results are summarized below. So we have some people did not drink any tea at all. Okay, so there are people who didn't drink tea at all. And then the probability of drinking type A and B and C is this. Okay, so this is and. They're using and, meaning the probability of A and B and C is 7 over 54. And so with those 3 events that we have, the 3 circles, there's going to be an intersection. That's really what they're saying. Okay, with the info they're given, we might as well just start with the Venn diagram already. We have 3 circles, okay, and they do intersect. They do have one common intersection, and this is A, B, and this is C. So first they tell us that there's some people who don't drink tea at all. I'll just put that outside and I'll call them X, okay? And then the probability of people who drink tea types A and B and C, that was 7 over 54. But do you see that we have 7 people? This is a probability. And so it means that these are 7 people out of the total 54 people they mentioned. And so here in the middle, we would have 7. Those are the 7 people. And then they tell us that 9 people drank types B and C. So 9 people drank types B and C like that. So when we're looking at that, we're looking at the intersection of B and C because they say and. Okay, if they say and, that is intersection. So that would be a total of 9 people drank this, but you already know that 7 people drank all tea types. And so because this needs to add up to a total of 9, you're just going to say the 9 minus the 7. Then 2 people here drank tea types B and C, but not A. Okay, so that would be the 2 that we have here. So that is for the intersection of B and C, excluding A. And then they tell us that 2 people drank types A and B, but not C. Okay, so A and B, but not C. So don't include C. And so they're referring to this intersection over here. And so we'll just say those are 2 people. Then 18 people drank type B. So 18 people drank type B, meaning everybody here, if you add them up, they will give you 18. And so to find the people who drank type B only, okay, then we would find that by saying the 18 minus the 2 minus the 2 minus the 7. 18 minus 7 is 11, minus 2 is 9, minus 2 is 7. Okay, so we have 7 people over here. And then they say no one drank types A and C, but not type B. So no one would mean 0 people, okay? So 0 people drank types A and C, so that's the intersection of A and C, but then they say not type B, so excluding B. And so that would be this over here. That means these people, there was 0. And then we have drinking type A is independent of drinking type B. Okay, so we're working with independent events here. Okay, so independent events work like this. So we're working with events A and B. If they say that A is independent from drinking type B, then this means that the probability of A and B is equal to the probability of A multiplied by the probability of B. Okay, so that's just what that means. And then we have the probability of not drinking type A or B is equal to the probability of not drinking type A or B or C. Okay, let's just put that down. So probability of not drinking type A or B. That would mean that you're looking at these circles. You're going to look at A or B. That would mean A and B added together. They're saying the probability of not drinking any of these ones. So what does that leave us with? That would leave us with the probability of drinking C only and then the people on the outside. Okay, so I'll still put it down here. This is the probability of not drinking type A or B. Okay, so not type A or B, that this is equal to 2 times the probability of not drinking type A or B or C. Okay, so this is not A or not B or not C. Okay, and so what this is going to look like here is we're saying when we're looking at A, B, and C, you see they're using the words or. So that would mean that you're going to include all these circles, right? And we're going to make sure that we do not take any of them because they say not A or B or C. So all of these, we're not going to include them. That would mean that is the outside, which is X. I just call that X. Okay, so that one is also done. Now the question in 10.2.1 says, calculate how many people drank type AT. Okay, so how many people drank type A? Do you see that to find that we would need to find the people who drank A only? Okay, so what information did they give us about A? I know that here they're giving us, but you know, with this work, it seems more like about finding this part. So we can use the first one. Let's try to use that. So to use this equation, we're saying the probability of A and B. Let me put it down first. And so the probability of A and B, okay, if we look at that, the intersection of A and B, that would be this, okay? This is where the circles of A and B intersect, this whole thing. And so it's the 2 plus the 7, but remember, it must be a probability. So it must be a fraction or percentage, or we're using fractions here. So this is just going to be 9 over the 54 people. The total 54 people is equal to the probability of A, which we don't really have yet. But you know what? We can just say probability of A. This is missing, no problem. I'm just going to call that probability of A, okay? So because it's just going to find that. Since they said calculate how many people drank type A, okay? And that's really what we're trying to find, type A. So I'm going to focus on that entire circle. Then multiply by the probability of B. So probability of B would be the entire circle of B. But the thing is, they already told us this, remember? We already had this and we were able to find the 7 because they said 18 people drank type B. So we know that the entire circle of B, they add up to 18 people. And so say times 18 over the 54. Okay, and this equation will lead us to that. Yeah, I see why. We didn't really need the Venn diagram, but okay. This is what we have. And let's find this. So we're going to need to get this alone. To do that, we need to get rid of the 18 over 54. You can decide to divide both hand sides by 18 over 54. That is fine. Or we can also do this. To get rid of this, we can multiply by 54 over 18, okay, on both hand sides, of course, because this is an equation. And let's get our answer. So this is the probability of A, and then it's equal to, do you see that? Yeah, I said 18 over 54. 54 over 18, okay? You must multiply by the reciprocal so that you can see that the 54 and 54 will cancel, 18 and 18 cancel. So here, 54 and 54 will cancel, and you have 9 over 18, which is a half, okay? So we just have a half there. So let's think about this. If the probability of A is a half, then how do we find out now how many people drank in A? So what the probability of A equals a half means is in this entire study, okay, this circle, if you add up everybody, they make up half the sample space, half of everyone in this study, okay, even including the people on the outside. We know that there was a total of 54 people. And so to find out the people who drank A, okay, in type A, this is simply equal to 54 multiplied by a half, because it's half of the total people. And so that is 27. And that is our answer. Okay, moving on to the next question. Then the last question says 10.2.2, use the given information to complete the Venn diagram provided in the answer book. So we already have the Venn diagram. It's almost complete. And we can just go ahead and fill it in. So if this is what we have, let's just fill in. You see in the previous question, we found out that the probability of, or really just the total number of people who drank type A, okay, there were 27 people. So it means that this entire circle should add up to 27. And so we can just say 27 minus the 2 and the 7, and of course the 0 is nothing. So minus 7 is already 20, minus 2 is 18. So that means there are 18 people here, and this is what we have so long. Okay, so to complete this diagram, do you see that this is missing and called it X, and this is also missing, so I'll call this Y. So we can actually give them names. They actually do have names. They named it for us here. Do you see that here they tell us that the probability of not A or B, right? So remember, you're going to look at these circles like this. You're looking at A or B. This is A or B, right? If you said find the probability of A or B, this is what you would find. Okay, so the addition in everything in circle A and circle B, that would be probability of A or B. Now they're saying the probability of not A or B, so everything excluding this. So that would be what is here in the circle of C, so C only, and the X. That's that all together. So, okay, I'm just going to have to name this one at least first. So what would this be? Okay, this, they actually gave us the name. They said 2 times the probability of, now forget the 2, look at this part. If you look at the probability of not drinking types A or B or C, then you would exclude the whole circle of A, exclude the whole circle of B, and exclude the whole circle of C, and you see how that leaves you with X. So that's what I'm going to call X. I'm going to say, let X equals this, and I'm just going to put it like that. Okay, let me just call it that. Let X equal that, and then we need a name for Y. Now, looking at this, they never really pinpointed at Y alone. Okay, they never really just named Y alone. Or at least what we are calling to be Y right now. So this is probability of not drinking A or B. That is just everything excluding this and this. And so do you see how that leaves you with the X plus the Y? Okay, so I'm just going to call Y the probability of C only. Okay, so let's just say let C only, or let Y equal C only. I'll just call it drinking only type C. T, okay, and then I can just go ahead and call that. They did name these people. They said these were people who did not drink any tea. So I'll just say people who did not drink any tea. Okay, so yeah, that is what we have there, just so that this makes sense. So the only thing that can help us to find these would be anything that speaks about C. And we already have that equation. It was this one. Okay, so this equation here, where we have the probability of not A or B, right? That is equal to 2 times the probability of not A or B or C. So let's see how we get this. Okay, so probability of not A or B, remove this A and remove B, and then you're just left with the X and the Y. So that would be these two. And so to find that, you just say the X plus the Y over the 54. Because initially when I saw this, I thought, okay, since they say the probability of not A or B, then I just excluded A and I excluded B. And I said, okay, that's why. But then I was like, no, but then this is still here. So that can't be the case for this. From what they're saying, probability of not A or B, that can't just be this. It's not C only. It's C only and then the people outside. Okay, so that is the X plus the Y. And we know that this is equal to 2 times the probability of not A or B or C. So that's not A, not B, not C. And then you see that that is actually X. So it's 2 times whatever X over 54 is. Okay, so right now with this equation, do you see how you won't be able to solve for X and Y right now? So let's take this a step further and just see what other info do we have. With C, there's not much info that we have. Okay, we have everything that we have, we've used already. We've put it in all the places it should be. The only thing that we do have is the sample space. We know that there's a total of 54 people in this study. So why don't we just add everything up together and we know it should give us 54. So that is the X people plus the Y and then plus everything else. I'm just going to say 18, 2, and then 7, 7, 2. Okay, it should add up to 54. Let's see what we get with all these numbers. Okay, so they add up to 36. So that means this X plus Y, okay, and then we'll just say plus 36 is equal to 54. So plus 36 is equal to 54. The only thing we can find with this is X plus Y. But that is actually, yeah, it's not a bad idea. Yeah, because we have X plus Y over 54, okay, using the info they gave us here. So we can simply just say, okay, we're going to take the X plus Y and we'll put that down and then take the 36 over. So 54 minus 36, 54 minus 36 is 18. Okay, so this is 18. So that means X plus Y gives us 18. And so if X plus Y gives us 18, that means this over here, this X plus Y over 54, that this is actually 18 over 54. Okay, which is going to be equal to, if you say 18 over 54, that gives us 1 over 3. Okay, so we know that this is equal to 1 over 3. So we can actually take this equation and we can work with it further. So I'm going to take it like this rather, instead of just like that. Okay, so I'm just going to say 18 over 54 is equal to, here we might as well just start, cancelling. So if you say 2 multiplied by, and there's the denominator of 54, it's the same thing as saying 2 over 54, okay? Because this 2 is in the numerator. And so we know 54 divided by 2 is 27. So we have X over 27 there, okay? 27. Do you see how this helps to solve for X? Okay, we can actually solve for X now. So we know that X over 27 is equal to 18 over 54 is 1 over 3. And finally, we can solve for X. So to solve for X, get rid of the 27. We'll multiply both hand sides of the equation by 27. And finally, X is equal to, what is 27 over 3? That is 9. Okay, so now we have X. And now we can also find Y. Okay, remember how, X plus Y, this is like a simultaneous equation. Okay, so now we know that X plus Y is equal to 18. So X plus Y, X is 9, plus Y is equal to 18. Okay, so here to solve for Y, we'll just say finally Y is equal to, take 18 minus 9, which gives you 9. Okay, so here, these are our two values. That's X and that's Y. So X is 9, Y is 9, and now we can finally fill in that Venn diagram. So we'll know that this should be 9 here, and that is 9, and that's going to fit everything we have. Okay, so that is our answer. That is 10.2.2, and that's the last question for this paper. So that is it for this paper, and I hope to see you guys in paper 2.